All right. Um, this is going to seem a little bit choppy the way I'm doing this, just simply because our book does not go in enough detail. I tried to start, as you can see here, I tried to start doing the lecture off of this, but guys, it's just not going to work. Okay. Um, our book is not giving us enough information, so I'm going to add to it. All right. Anyway, erosion and deposition, gravity's role. We all know, and you can see by my arrow here, gravity pulls down. All right, gravity is going to pull all loose material down. It gets help through streams and other. When I say stream, that means all surface water streams. A stream can be the Mississippi River. A stream could be Clear Fork River. A stream could be a little creek that runs through your backyard. They're all called streams. All right. So erosion and deposition. Our book talks about gravity's role, which is great. And gravity gets help. Streams would not flow and glaciers would not move without gravity. Gravity is what moves those processes or drives those processes. So erosion by water, and this is where I was talking about, it's going to be a little bit choppy. I'm going to flip now to some notes, and I'm going to go through some of these notes and try to explain what's going on with water, running water and groundwater. And what they're talking about in our book right here is running water. We already know a little bit about the water cycle. All right, and here we go, stream flow. The ability of a stream to erode and transport material depends largely on its velocity. Gradient, this is where gravity comes in. Gradient is the slope or steepness of a stream channel. The higher the gradient, the steeper the stream channel, okay? Now, when I tell you that, and we can talk about the Clear Fork River because we're all pretty familiar with it. The ability of a stream to erode and transport material depends largely on its velocity. The more water in that channel of the Clear Fork River, we know the higher its velocity is. We see that all the time, all right? Sometimes the water in the Clear Fork River is cloudy. It's carrying erosional material. Sometimes it's clear. When it's moving slow, it's clear because it doesn't have the force necessary to move erosion agents. All right. So the velocity is the key here. Channel characteristics. The stream channel is the course the water in a stream follows. There's different shapes, sizes, and roughnesses to stream channels. Even in the Clear Fork River, it's different around Gatton Rocks than it is in other places. It's rough around Gatton Rocks, all right? Discharge of a stream is the volume of water flowing past a certain point in a given unit of time. We don't really need to know discharge apparently here. But the higher the discharge, the more sediment or the more erosional material it'll carry. Changes from upstream to downstream. While a gradient decreases between a stream's headwaters and its mouth, that means where that stream starts, the gradient is usually steeper. And discharge, while gradient decreases between a stream's headwaters and mouth, discharge increases. So in other words, if the Clear Fork River is running into the Ohio River, it has a higher discharge into the Ohio River. Its discharge increases as you get closer to the stream's endpoint than it does at the beginning or where it starts. Profile of a stream is a cross-sectional view from the head, the mouth. Profile is a smooth curve, and gradient decreases from head to mouth. That means where the headwaters is where it starts, the mouth is where the stream ends. So wherever the Clear Fork starts, that would be its headwaters, and its mouth, where it flows into the Ohio River, is where it ends, okay? And usually gradient is greater at the head than it is at the mouth. Changes from upstream to downstream. Profile, a tributary. A tributary is a stream that empties into another stream. So the Clear Fork would be a tributary to the Ohio River. Factors that increase as you go downstream, velocity changes, discharge changes, and so does the channel size. Here's a prime example, okay, sea level and streams. Here's the stream coming down. You can see tributaries running into the main trunk right here. The main stream is right here, and these are the tributaries coming into it, okay? Notice that at the headwaters or the head of the stream, it's a lot steeper than it is down here at the foot of the stream or at the mouth where it comes out. The difference is these streams up here are a lot smaller, and as they join together, the stream becomes larger until it hits the mouth, and this is where a lot of our erosional material is deposited. More changes. Factors that decrease downstream include the gradient or slope and the channel roughness. Here's a meandering river, and the Clear Fork River is on its way to this. It meanders a lot as it goes through town. Lots of loops and twists and turns. The lowest point to which a stream can erode is the base level. The ultimate is the sea level, temporary or local level. That could be, it can erode down to where it is hitting that base level or that bedrock to where it cannot dig down anymore. A stream in a broad, flat bottom valley that is nearby its base level often develops a course with many bends called meanders. And since the Clear Fork meanders through town there a little bit, and it does have a lot of twists and turns, I would say it is pretty close to its base level. All right, so stream erosion. Streams generally erode their channels, lifting loose particles by abrasion, grinding, and by dissolving soluble material. Then it deposits this. A stream's bed load is a solid material too large to carry in suspension. The capacity of a stream is the maximum load it can carry. So we have a bed load. What is it carrying? How much can it carry is capacity. Deposition occurs as a stream flow drops. So when the Clear Fork is moving really fast, it has a lot of dirt and debris in it. And as it slows down or the water level goes down, as the stream slows down, its capacity changes and particles start to fall out of it. As those particles fall out, that is its deposition. All right. Think about putting some paper on a table with a fan. If you kick the fan up on high, the fan's going to blow all the paper away. We're going to crumple up some paper and put it in front of the fan. If we turn the fan down, though, on low, the larger pieces of paper will not blow away like the smaller pieces of paper do. That's kind of what goes on with the carrying capacity in a bed load. As the stream slows down, as the fan blades slow down, they cannot carry or push as large material. It'll be smaller. And when the larger pieces fall out, this is called deposition. Or alluvium, we call those deposits alluvium. Deltas are accumulation of sediment formed where a stream enters a lake or an ocean, and a natural levee parallels a stream and helps to contain its waters except during flood stages. Stream valleys, that's what the Clear Fork is a stream valley. Narrow valleys, a narrow V-shaped valley when it first starts shows that stream's primary work has been downcutting towards its base level. Features often include rapids and waterfalls, and this is the beginning of a V-shaped valley. Notice how it's V-shaped, okay? It's V-shaped. As the water flows, it cuts the banks away, and these rapids and the waterfalls will eventually disappear. The other thing that happens is these are natural places for glaciers to flow through. Glaciers flow just like water, and we'll talk about those next, I believe. But glaciers are going to come through here just like water does. And they reshape that valley from a V to a U shape. Wide valleys, stream valleys, and that's kind of where we are now, is a wide valley. Streams are near base level. Downward erosion is less dominant. Stream's energy is directed from side to side. And the floodplain is the flat, low-lying portion of a stream valley subject to periodic flooding. And we know in our Clear Fork River there that it floods to the east, or I'm sorry, it floods to the west of where 96 and 13 hit. That west end of that on the other side of the road there, on the other side of the stream, that is a floodplain. It always floods there when the stream overflows, Clear Fork overflows. Wide valleys features often include meanders, cutoffs, and oxbow lakes. Well, we know there are meanders there, and here are some meanders. This almost reminds me of where the Clear Fork comes down, where 13 goes along. Here would be the bridge going into town. Notice it kind of looks like this. Then it comes around, and there's that little white house right here. Then the flow goes on out. We don't have to worry about oxbow lakes at this time. Just remember that we're talking about cut up. What happens here is it erodes away. It erodes away, and it eventually will fill in with sediment, and you get this little loop out here called an oxbow lake from erosion. All right, so let me just glance down through here. Here's the Ohio River flooding. All right, so I think that's it for this part. I'm going to pause. I'm going to bring up another. You won't recognize the pause, but I'm going to, and we're going to look at the book, and then I'll bring up some more notes. Okay, so the book now is talking a little bit about wave action. Right here would be the wave action. I've covered this part right here, erosion by water, rivers and streams, and that. Wave action, as the waves crash up against the shore, and this is happening in Lake Erie in Cleveland. People are losing their backyards, sometimes 4 foot a year. What is happening is the water comes up, hits this, and breaks this apart and drags it back in. As the lake or the ocean hits the shoreline, it's going to pull it back out, and it goes back and forth and back and forth, and it eventually wears all of this away. Let's jump down now to glacier erosion. Okay, now the next part it talks about is glaciers. First of all, and I think we have a chapter about glaciers, but in case we don't get there, I'm just going to kind of go over this a little bit. Glacier is a thick ice mass that forms above the snow line over hundreds of thousands of years. During the last ice age, the glaciers that covered Ohio were anywhere from 1.5 to 2 miles thick. So think about the weight of a 2 mile tall glacier. Crazy. So anywhere from a mile to 2 miles, mile and a half, someplace in there. That's how thick the snow was, how deep the snow was, and the glaciers, okay? Valley glaciers, that's what would have been in our area. Valley glaciers would have scraped that out. So there are also ice sheets, North and South Pole currently, I don't know what happened there. Ice sheets are huge. They cover Greenland and Antarctica at this point, okay? So here's my ice sheets covering this. How do glaciers move? And this is important to understand how they also erode. So there's plastic flow, which involves movement within the ice, and then there's basal slip. And basal slip is, there it is, due to gravity. Glacier budget, we're not going to talk too much about right now, but this is what goes on. Notice this right here, this area, and calving, if I can get that far, I will. But notice this area. This is called the zone of wastage, and what happens is this is starting to slip. So it's causing the glacier to grow. As snow piles up in the zone of accumulation, it pushes this downward. Here's the other thing. Inside inside this glacier. Um, After about 50 meters down, this is slush, like a slushy you'd get at a 7-Eleven or whatever. These are slush material, like a slush puppy inside of here. When I get these cracks down in here, when it cracks, that slush moves out. The slush moves out, piles up here, refreezes, causes this to slide down a little bit. That is plastic flow. Basal slip is just, this gets so heavy and the slope is steep enough that it just slides down. And when I get that is when I get the crevasses. And these crevasses, I know on TV and that they'll show them, thousands of feet deep and people falling through them hundreds of feet down. Untrue. They can only go so deep because what happens as these crack, they fill up with the slush puppy material and refreeze. So these are not endless caverns. Crevasses are not endless cracks in the ice that are, 300 or 400 feet deep. They can only go so deep. Now, calving, all calving is this. If this ice moved right here to the edge, and let's say this here would be the ocean, it's going to float out on the ocean a certain length, but then the ground can't support it anymore, and it'll break off and go into the ocean. That's what's going on here. You can see, look at the ground here. You can see the earth. Well, that's over here too. You just can't see it because of the ice. As the ice moves down across there, it's going to lay out over the ocean, and these great global warming pictures they show you are not really global warming. It's calving. It's a natural process where the ice has gone to the edge of the ocean. It's coming out over the ocean. There's nothing underneath to support it but this water, so it breaks off and falls into the ocean or into that body of water. Normal process. Don't be confused when, global warming, look at the ice melt. Well, yeah, it does melt like that. And if there's a lot of calving going on, that means there's extra snow in the zone of accumulation. And again, I'm on the bandwagon of a new ice age coming, a mini ice age, not global warming. So calving is a natural process. Glacial erosion. Here we go. Many landscapes were changed by the widespread glaciers of the recent ice age. How glaciers erode. Plucking. First of all, what happens is as that glacier moves along, let's try to see if... All right. What happens is as a glacier slides along, and right here, as it slides along, it's going to pick up debris, and you can see the little rocks in the bottom of the glacier lodged down in here. They're getting that from this bedrock. That is called plucking. It is plucking these pieces up from the bedrock, and they get in here. That is called plucking, and that's part of the erosional process. All right, so after it lifts up these rocks, this plucking, the bottom of this glacier becomes like a piece of sandpaper. All right, and as it moves along, it's going to tear stuff up. That is called abrasion. Some of it will be considered rock flour, pulverized rock. Looks just like flour that you would get from the store, but it's just rock flour. Striation, grooves in bedrock. All right, so I'm going to look real quick and see if I can find some pictures of this. I should have some someplace. Hold on. All right, so here's some abrasion from a glacier. You can see how it plucked stuff up, plucked rocks and that up, and as it came across this rock, it acted like sandpaper. And there's some abrasions here. Let's see. There should be some more. I have more pictures here of abrasions. Let me pull this one over, maybe, if it'll let me. Here's another abrasion. You can see how a glacier slid across here and just eroded away. giving us some abrasions there. See what else we have, if anything. I know I have more. Here's another abrasion. These are kind of cool. This is really cool. But it came through, that glacier came through, tore this all up. And you can see these loop-de-doo abrasions, kind of cool stuff. Let's see what else we have. Or if I can find any other things that I would like to show. Other things that happen too. Really cool that they leave behind glaciers. They'll leave behind an erratic. It's called an erratic. This is not in our book in that, but this is part of the erosional process too. Check this out. A glacier, that's how powerful. Imagine, like I said, a 1 to 2 mile high block of ice. Look at this, pluck this up. Probably up in Canada, it's a piece of granite. And there's no granite around here in Ohio unless it got left behind by glaciers. But this is a type, when we're talking plucking, we're not talking just tiny little pieces of rock. Imagine this cruising across the ground. You can understand how abrasion takes place because of things like this. Look at that. Imagine that big chunk of granite cruising across this and chewing it all up. So that's kind of the way a glacier is eroding things away. Let me go on to the next section in the book and we'll go. All right, I found a couple of really good models on plucking. This one is kind of, it's not real focused just because I had to blow it up to get it on the screen. But as this moves down, it's showing, you can see here how it's plucking. It's pulling the bedrock up. It's pulling the bedrock up and it's getting lodged in the ice. Here's another, I have another one here too that if I can find it right here. As this moves along, it's picking up these pieces. It's plucking these pieces up and using them as you would use a piece of sandpaper. Notice here how I come up on a slight slope, and then gravity pulls this down and causes these crevasses to form. All right, and those crevasses, again, they can only be, I forget the exact distance, but it can only be so deep because of that slushy material that's down in there. All right, so wind. Landscape shaped by wind and wind erosion. Wind erodes the desert in two ways. It erodes everywhere, but it is most prominent in desert areas where sand can be blown. And it's used, again, just like sandpaper or sandblasting something. It tears things up. So deflation is a lifting and removal of loose particles such as clay or silt, and this produces blowouts. Let me go back here. Deflation. Here's deflation. What happens is I have this solid material, these rocks, with a bunch of loose material in it. And what happens is as the wind blows through here, it takes the loose material and transports it away. And as it transports away, the larger particles get closer together. All right? It's transporting the loose material away. The solid particles are the larger particles that the wind cannot move, end up crushing themselves together because of all of the loose material being taken away. And we get what's called desert pavement. That's why out there in White Sands, New Mexico, where they drive those rocket cars and stuff to super high speeds, breaking speed records, land speed, they do it out there because it's covered with desert pavement. And this is just, it's better than pavement on the road, driving down the road. It's nice and smooth, and it works very well. So this is deflation. This is how wind deflates the ground, and it causes desert pavement to be created. Also, abrasion. Wind can create landforms when it deposits sediments. This abrasion, I should have went back a little bit. There's no pictures of abrasion from wind here. But wind will abrase, just like I said, just like a sandblasting. And if you've ever used a sandblaster, guys and gals, you'll know it doesn't take long to get what you want there. In the desert, too, we get sand dunes, which are wind deposits where they pick up loose material and deposit it. Right here, you can see a dune in New Mexico's White Sand National Monument Park, all right, where the wind brings up the sediment. It brings it up, and as it gets to the top of the dune, it dumps it over the edge, all right? And these are all sediments here. Here's some cross bedding in Navajo National Park in in Utah. You can see the striations here. Almost looks like a glacier went over it, but these striations are caused by the wind carrying sand. And then there's different types of deposits. This, you're talking in the Middle East, these star deposits, and what I'm telling you, they're big. They're the biggest ones. If there was a car or a Jeep sitting here, it would be like a little speck. These things are huge, hundreds of feet high, hundreds of feet long, and there would be, if you were a person standing here, you'd just be a little speck on this model here. Other types of deposits are bracken deposit, and you don't need to know this. These are just different types of sand dune deposits. Barcans, longitudinal, transverse, and yes, they look like waves, parabolic waves, and barcanoids and stars. And I think, let me go back to the book here real quick and see what's going on. All right, the last little bit here is erosion by living things, especially human beings. You can see here what would take maybe 100 years, they're going to destroy it in a few minutes just by digging and doing that. So we have to be careful. These great sandstorms of in Oklahoma and that back in the, I think it must have been the 30s, this is caused by human beings and the things we do to, we had all these fields with nice greenery and trees in that. They were all cut down and made into farmland. And those great storms that happened back in that time in the Dust Bowl was caused by deflation. There was nothing to hold that loose soil down. And it just caused a massive deflation. And so erosion by living things, mostly with humans, we have to be careful what we do so we do not destroy the environment like that again. All right. So that's pretty much it for these notes and the lecture. They're both combined here. I hope this helps you guys.